Welcome AP Physics Mechanics students. Today's review topic is momentum. In today's video, we're going to review the definitions of momentum in the momentum unit, momentum and impulse. Then we're going to learn the main idea. There are actually two main ideas here, one regarding impulse and the other one regarding momentum being conserved. Then we're going to also review 2D collisions and the idea of center of mass. So the definitions. Momentum, which has the symbol P, lowercase p, unlike power, capital P in the energy unit, lowercase p, mass times velocity. And I didn't put the vector signs, but all of these quantities today are vectors. Unlike with energy, those were all scalars. And what that means is the scalars have no direction associated with them. So whether you're moving north, south, east, or west, you have the same amount of kinetic energy. Okay, it doesn't matter the direction. Momentum and impulse are different. Momentum, the direction matters. So say a momentum of 10 to the north is different than a momentum 10 to the south. So you need to know the direction. The mass, obviously, of an object is in kilograms, and the speed or velocity is in meters per second. The units of momentum, therefore, are kilogram meter per second. There is no other unit. We don't rename it anything like when, in the case of energy, when we had work being force time distance Newton meter, we called that a joule. Not so with momentum or impulse. The units are just the units of the terms in the equation. Impulse is given the symbol capital J. As I said, it is a vector because it depends on the net force, which is a vector. But it's the most basic definition is net force times time measured in Newton seconds. You could think of it as the effort you put into something when you are trying to get it moving or to stop it. Okay, so the harder you push, the more impulse. The more time you push for, the more impulse. Okay, and we'll see in main idea 1 what that does, what impulse does. But force may not be a constant throughout the motion of the object. If it varies with time, then you need to convert this idea into an integration. So what we do is we multiply force times a tiny time fragment, like say a millionth of a second, over which the force is relatively constant. That gives us the Newton seconds, the impulse or the effort during that millionth of a second. Then you add up all those contributions over the various millionths of a second from one time to another, summing up infinitesimal values, and you get the net force times time. Well, also, as you know, when we studied calculus, when you integrate, that's the area under the, it gives you the area under the curve of a force versus time graph. So impulse is also net area. Similar to work, when we did force times distance, or F dx integrated from one x coordinate to another, giving us the work. When we do force times time, we can, if we have a graph like this, and it's we have formulas to calculate the areas because it's not a curve but some kind of linear pattern. We could have any area above the t-axis count as positive impulse, and any area below the x-axis or the t-axis count as a negative impulse. So positive and all the areas above, negative all the areas below. Sum that up and you get the impulse. Well, what does impulse do? This is the first main idea right here. Actually, it's the only main idea because I'm going to explain how the other main idea actually can be determined through this main idea. But what it says is that the impulse is equal to the change in momentum. And that, like a lot of things in mechanics, makes sense, common sense. If you push for with a lot of force over a long time, the object will gain a lot of momentum. If you push with very little force, very little time, small impulse, the object doesn't gain or lose much momentum. Okay, so the harder, it's basically your effort changes the momentum. And I'm going to show you a couple examples of calculations with this concept. So here's a kind of a classic calculation where you have a ball pitched, so maybe it's like a baseball or a softball, pitched at 30 meters per second, and it's hit back by a batter with 45 meters per second, and that impact lasted 8.5 milliseconds, milli being 10 to the minus third, and the question asked for the net force. So the first thing I want to point out, again, everything in this topic, momentum, impulse, forces, are vectors, including the velocities. So even though this was given as 45, we have to realize it's actually velocity of negative 45 because it's in the opposite direction of the 30. This is positive, that must be negative. Pitch the ball, you hit it back, negative. Okay, opposite sign. All right, so now knowing that, we're going to move on to the calculation. Okay, here we are. This is impulse, right? J, force times time, equals change of momentum. I expanded out, which I recommend you do also, as mv final minus mv initial. So you see, I put in the time of 8.5 milliseconds. That's 8.5 times 10 to the minus third. So that's why the decimals moved over. And then the negative 45 for the final velocity, and a positive 30 for the original initial velocity. And then you just do your algebra. So that's a kind of a classic impulse calculation. Let's take a look at another one, a little bit more sophisticated. A 4 kilogram mass at rest experiences a force given by this function, which is the downward parabola because of the negative t squared, from 0 to 4 seconds. Determine the impulse and the final speed or velocity of the object. Did I write that it started at rest? I guess I didn't. I should have wrote that it started at, oh yeah, at rest. Okay, that's good. So here's a graph of the function. From 0 to 4 seconds, it's this downward parabola. Peaks out at 24 actually, if you were to plug in at 2 seconds right there. Not important, but I'm just pointing that out so you have a little visual here. So to find the impulse now, we can't say force times time because the force varies, so we got to use the force times time integrated instead. So I write out my equation, then I plug in my force function, and I integrate. The details of the integration, I add 1 to the exponent, make that cubed. And then I divide by that new exponent. 6 divided by 3 gives me 2. And then, of course, the minus sign. Here, t to the 1 power integrates to t squared. And then I have to divide the 24 by 2 to get 12. Just a simple power rule. Plug in the limits, and you get 64 Newton seconds is the impulse. Okay? So that's the first requirement. The next thing, the final speed. Well, now we use that main idea. That impulse is equal to the change of momentum. So mv final minus mv initial, object was at rest initially, and you get the final speed. So similar to the previous example, only the impulse calculation was a little bit more sophisticated with an integration. Okay, so on to main idea 2. Okay, here it is. Well, last topic we had the idea that energy was conserved for an isolated system, the total energy. And the same thing with momentum. We have this idea, I wrote it out as an equation this time, but this has to be an isolated system. In other words, there can be no friction in the track, no air breezes, the track can't be tilted, level frictionless track, then the initial momentum of the system is equal to the final momentum of the system. Now another thing that's in the curriculum is that they list an objective that indicates that you have to know why momentum is conserved. And so here's the y over here in this little diagram. So A and B are colliding with a spring between them, that's what that is. And what happens then when the impact is A pushes B forward. And then Newton's third law. If A pushes B forward, B pushes A right backward. Okay, for the same amount of time. So the forces are the same but opposite for a certain amount of time. So I could say that mathematically the way I write with how these arrows are is that this is in the negative direction. So I put a negative force times time equals the positive force times time of B. Okay, so that's basically Newton's third law. And then multiplied by time. Now, main idea 1 is that force times time is change in momentum. And I move the minus sign over with B over here. I could do that mathematically. This actually comes from Newton's second law. This is the third law. Forces equal and opposite. The second law is that there's an acceleration caused by the force which changes the momentum. And so you can see that the loss of car A, because it's moving forward and it's colliding, so it's going to lose momentum. Minus sign means the other thing is going to do the opposite of a loss, which is a gain. So the loss in momentum of one car is the gain of momentum on the other car. And that's basically saying Pi equals Pf. Some numbers. Let's suppose this has a momentum of 10 and this has a momentum of 2. They crash. This loses, so they have 12 together. They crash. This loses 2, so now it's going 8. Well, that's got to pick up 2. So now it has a momentum of 2, not 2, but 4. So we have 8 and 4 after, 12 again. So 10 plus 2 before, 8 plus 4 after, 12 equals 12. Pi equals Pf because the loss of one car is the gain of the other. So that's part of the curriculum. I don't know, maybe they'd ask you to describe that out with sentences in a problem. But more likely you'd be analyzing collisions. This is more likely here. First thing, definitions. A perfectly inelastic collision, you need to know that definition, is when two cars or two objects crash together and they stick together. And they move together as one object in unison. So the final speeds of the two are equal. In such a collision, like cars with Velcro between them, the momentum's conserved as long as the system is isolated. But kinetic energy is lost. Energy isn't lost. Some of the initial kinetic energy, maybe we had 10 joules and we only have 8 after, because 2 joules were converted to other things like sound, or maybe crushing the car down takes work. So total energy is conserved, but kinetic energy is not. But in an elastic collision, and we don't need perfectly elastic, that's redundant. Elastic implies that yes, the momentum's conserved, as with inelastic, but the kinetic energy doesn't change. Whatever kinetic energy the system has before impact, it has it after. The way to achieve this is with what we call ideal springs, which really don't exist, or magnet to magnet that repel and the cars never hit each other, or electron to electron. Maybe you make this negative, and then it repels and then goes without touching. So that would be an elastic collision. Here's an example of a kind of calculation you might encounter with main idea 2, momentum being conserved. So we've got mass m moving v0 hits and sticks to a stationary 3m. So they stick together, determine the final speed, and then the change in this ratio, change in kinetic energy over initial kinetic energy. So here's a diagram of what's happening. M moving at v0 targets this mass not moving. After they stick together, one mass, 4m, and moving at a final speed. The main idea, Pi equals Pf. It's an isolated system. So before the impact, you can see there's only one thing moving. That's this mv0. I could have put plus 3m times 0 on this side of the equation too, but why, right? It's 0 anyway, so I could just leave it off. After, I can say that these objects combine to be one object, m plus 3m, or 4m moving at one final speed, and you get a quarter v0. Now, to find this ratio, change in kinetic energy over initial kinetic energy, what I do is I calculate the kinetic energy of the system before impact and after impact. So 1/2 mv squared is the kinetic energy of this car coming into the impact. After the impact, we have 1/2. The object's mass is now 4m. That's what's moving, the two cars combined. And they're moving at v0 over 4. If you do that analysis carefully, you get 1/8 mv0 squared. So you see a loss of kinetic energy. Again, that energy became other forms. It wasn't lost to the universe. Okay, this delta K over K initial. So what you do is you take the final kinetic energy and you subtract from that the initial. And I just went ahead and find a common denominator. 1/2 is like 4 over 8. Same thing, 1/2, right? And then all over 1/2 mv squared. If you're careful with your subtraction and division, you get -3/4. That means that 75% of the kinetic energy was converted to other kinds of energy, and only 25% of it remained regular old kinetic energy. Okay, so that's main idea 2, momentum being conserved in a calculation example. All right, tucked in within this momentum topic. Oh, also, I was about to go on to center of mass, but I forgot. I also wanted to mention a little bit about 2D collisions. Again, in these videos, I don't want to get bogged down into too much detail. It's just going to overload your mind anyways, and you won't retain all that. So I just gave a very scant, brief analysis of a 2D collision. Hopefully it refreshes the main idea. If such a collision comes up on the AP, you'll have the main idea refreshed, and maybe you'll be able to work out the details. So let's suppose we got object A coming in with 10 units of momentum, and this object's stationary. So this is like maybe two spheres in outer space, and they crash together. This is the impact point, and then A kind of ricochets off like this, makes a kind of a left deflection, and B goes off to the right of compared to the original direction down in this direction. So what happens is momentum is conserved in both the X and the Y direction. And so when I look at what's happening after, you would have to, on a typical problem, calculate out these components using sine and cosine, maybe if you know these velocities or something like that. But I'm just showing you the net result. Notice in the X direction, this ball, if it has 6 units of momentum, we used to have 10. We cannot lose momentum in the X direction. That means while this one ball, the first ball A, lost 4 units of momentum, the other one picked it up. And so what we have is 10 before and 6 and 4 after, which is 10 in the X direction. In the Y direction, if you look at what was going on before, we had no momentum. And then if this ball suddenly ricochets up with 3 units of momentum going up in the Y direction, this one has to ricochet down with -3. So we have 0 equals +3 minus 3, or maybe plus -3. We have 0 before and after. P is conserved in both dimensions. So a 2D collision is simply 2 momentum problems happening at the same time. One problem in the X direction, one in the Y, but Pi equals PF in both dimensions. We could go 3 dimensions too and then have J hat also here. But, 2 is enough to get the main idea. All right, last concept for today is center of mass, kind of tucked in with the momentum unit. So there are 3 ways to find center of mass. What I say, inspection. I'll show you with an example what that means. Using this formula for discrete masses, like if you have a bunch of, on a light stick that has very little mass, you have a bunch of spheres glued onto that, all at different X locations, all of different masses. What you do to find the center of mass is you add up the products of the X coordinate times the mass at that X coordinate, add that up for all the objects. If there are 10 objects, you have 10 terms up here in the top. All divided by the total mass. That gives you this. So it's like a weighted average. If you know how to calculate grades, quarter grades, it's kind of like a weighted average. Now, sometimes you need to find the center of mass of a bar, and the bar is non-uniform. So like if I take a single piece of steel and I just have a bar that's uniform, I know the center of mass is right in the middle. I don't need to do any calculating. But what if it's made of, like in class when we study this, it's made of wood, and I left one end soaking in a bucket and this end is up in the air? This would be more waterlogged, and the water would gradually be rising up here but evaporating, so we'd have some kind of density function. That's what lambda is. It's some kind of function. We'll see that in an example problem later. So it varies of how much concentrated mass we have throughout the bar. The way you calculate the X center of mass is by converting this to an integral. Notice what we're doing is we're dividing by the total mass, and then we're adding up the mass times its X coordinate. So here's X times the mass at that coordinate. How is that the mass? Lambda is the kilograms per meter. And then you multiply by the length of a tiny dx of the bar, like a millionth of a meter. So you have kilograms per meter times meter gives us the kilograms in a small slice of dx of that bar. So we're adding up x times mass, adding that up just like here, and then dividing by the total mass. So they're kind of the same formula. All right, so let's take a look at 3 quick examples. What do I mean by finding the center of mass by inspection? Right here. What does that mean? It means that on a multiple choice test, sometimes they give you the shape, an object, and they ask, well, where's the center of mass most likely to be? So what I have here, the picture showing a bar that's bent like this. Maybe it's like a coat hanger. Oops. And then what I also added are just some very light grid lines for reference. So this grid line goes through the halfway point in the vertical direction. This grid line goes through the halfway point in the horizontal direction. And I put 5 dots here. And what you have to realize is that this is a two-dimensional center of mass problem. The center of mass will not be in the middle because we have more mass toward the bottom. Here this is balanced. So the center of mass of this piece is right here in the middle. But then we've got more mass down here. So that's got to shift it down below this horizontal line. That leaves us B and E as choices. And then if you look at this midpoint, if we had another bar over here, then everything would be balanced horizontally. We'd have mass here, and then this balances in the middle, so the center of mass would be here. But since we have this that's unbalanced over here, that shifts the center of mass more to the left. So it's below and left of the center of the object. So choice B. That's by inspection. You would just look at that, boom, pick a choice within a couple seconds, and move on to the next question on a multiple choice. All right, example 2 is more of a calculation. So I've got a bar that's mass is considered negligible, so it's very, very light, maybe like carbon fiber. And these are blocks of metal, M at the origin, and that X equals capital D, we have 4M, maybe a kilogram and 4 kilograms or something like that. So the way you find the center of mass, I didn't write out the formula, but it is this one here, right? So, and then I take the X coordinate 0 times M plus X coordinate D times 4M all over the mass of M plus 4M, and I get an answer. Center of mass is at X equals 4/5 D right here. That's the center of mass somewhere there, okay? And the last one shows how to calculate the center of mass with integration. Okay, so I've got a 3-meter long bar, 7.5 kilograms, and here is my function, 1 plus x, that's a period at the end of the sentence. And what's the x center of mass? So notice that if I have a bar like this, at this end, the lambda is 1. At the 1 meter mark, because the bar is 3 meters long, at the 1 meter mark, then I have density of not 1 over here, but 2. At the 2 meter mark, the density is 2 plus 1, 3. At the 3 meter mark, it's 3 plus 1 or 4. So it's getting more dense as you go over here. That's what that function is saying. All right, so we use the formula that I had given you earlier, 1 over 7.5, 1 over the mass. And then I integrate x times lambda, lambda being this function, 1 plus x dx. So I distribute that x, which gives me x plus x squared. And then I integrate that from 0 to 3 meters, the length of the bar. Now x integrates to x squared over 2, and x squared integrates to x cubed over 3. And I have my limits to now plug in. So I plug them in there. Okay, and I churn out that solution, plugging in 3 into the formula, and then 0 into the formula, and I get 1.8 meters. So this bar, 3 meters long, remember it's more dense here. The center of mass is not at 1.5, but 1.8 somewhere here, because again, the mass is more concentrated at this end. So that's today's review lesson, okay? A reminder, just a summary, what we went through. We learned some definitions, momentum and impulse. Those are the ideas. We learned the main idea with impulse, which is actually, could be thought of as the single main idea of the whole unit, that impulse, force times time, changes momentum. For an isolated system, there's no impulse, so there's no change. 0 is the change in momentum. In other words, Pi equals Pf, which is main idea 2, right? So we could just say that impulse is 0, so no change in momentum, so Pi equals Pf. We could use main idea 1 to generate main idea 2. We learned that. And then we briefly looked at 2D collisions and the concept of center of mass. Okay? So that's today's information, today's unit that we reviewed, momentum. And I'll see you in the next review video.